This angle over here, guys, this is nothing but d theta. And this over here, this line and this dotted line, this is nothing but the radius of curvature. You can write it as r. Hi everyone, this is Manas, your friend and tutor, and guys, in today's session we are going to take a look at theorem number 2 from the moment area method. If you haven't seen my previous video, well, that was based on slope calculation at any point on a beam. This particular video, rather today's video, is going to be based on deflection, or should I say displacement of any point, right, on a beam when it is obviously loaded. So let's take a look at that. And first of all, let me just set up the environment. Let's say we've got a beam, we've got supports, and we have also got a hypothetical load, right? It's a uniformly varying load, and what we'll try to do is, let us first of all try to listen to what the theorem has to say. Okay, let's take a look at the theorem first of all, and these are the 2 points obviously which we'll be analyzing, right? Keep watching, the animation is going to be beautiful. Don't miss out and watch this video right till the end. Promise you, I make a claim right now that once you've seen the entire video, you would be able to solve any problem, or you would rather be able to calculate any displacement or deflection from any beam, be it an overhanging beam or a cantilever beam, कुछ भी हो सकता है, calculate कर लोगे आप बिंदास, बिल्कुल टेंशन मत लीजिए, right? So there is going to be an element also. Anyway, we're not worried about that. Let us take a look at the theorem and let's read it. So it says the vertical distance between the tangent at point A. Okay guys, so we'll be reading the theorem, and also I'll be demonstrating you with the help of an animation. Just take a look, okay? Simultaneously both the things will happen. So here is this elastic curve. Vertical distance between the tangent at a point A on the elastic curve. So let's say we've got 2 points, that's point A and that's point B, and tangent at A. What is it saying? Vertical distance between the tangent at A and tangent extended from another point B. So this is that vertical distance, right? It is talking about this distance. It equals the moment of area. Things are starting to get confusing. Moment of area. Have you ever heard about moment of area of what? Moment of area under the M over EI diagram. Now guys, if you have an in-depth knowledge of center of gravity, of centroid, you must have come across the moment of area, right? Moment of area. Yes, you heard that right. You must have heard about moment of a force, but now you should also know that there is moment of area. And as far as this particular article is concerned, theorem 2 is concerned, you also will learn what exactly moment of area of M over EI diagram is. I can completely understand, I can completely sympathize that right now you must be in a state of confusion, but don't worry. Keep watching this video right till the end and all your confusions will fly away. Don't worry, just keep watching, don't worry. What is it saying? Let us read that once again. Vertical distance between the tangent at A, tangent at B, this is that vertical distance. This vertical distance is nothing but the moment of the area, right? Moment of the area under the M over EI diagram between these two same points. You'll understand everything, right? Here also, this is T A to B and this is T B to A. So there is a proper way of reading this. What is T A to B? T A to B, this should be read as vertical deviation of the tangent at A with respect to another tangent from B. And guys, in the same manner you can read this. This is nothing but the vertical deviation of the tangent at B with respect to the tangent at A. Okay, so that's one way of looking at it. And this, by the way, is nothing but equal to the moment of the area of M over EI diagram. But what is that? What the hell is moment of area of M over EI diagram? In the previous session, in the previous lecture, you know what is area of M over EI diagram, and that was equal to the difference of slope at any 2 points on a beam or on the elastic curve. But this time, moment of area of that, well, let's see. Let's rather see the proof of theorem number 2. For that, what we'll try to do is, again, see this, we've got 2 points over here. Let me just show that to you, point A and point B, and let me just have an element dx. focus. You need to focus now. And here is this elastic curve. Guys, please pay attention. This is going to be super, super important, right? And let me tell you from the outset that the beam, if the beam is initially like this, the maximum it would deflect like this in this fashion, right? I mean, it cannot be visualized even by the naked eye. But here you can see the deflection is pretty much. It is exaggerated. ऐसा बनाना पड़ता है. Otherwise आपको समझ में नहीं आएगा. मैं construction नहीं कर पाऊँगा, right? The curvature is quite huge. You can see this. Okay, the curvature is quite huge. Why? The reason being very simple. We need to prove a lot of things and we need to make a lot of construction. That is why it has been done like this. Okay, if I make it like this, then there will be a lot of problems. You won't be able to understand anything. Anyway, remember this. Secondly, there are going to be points over here that's A, that's B, and now let us make a tangent from A. Just take a look. Very interesting. Tangent from A, then tangent from B, and here we go, tangent from A, and this is going to be tangent from B. This over here, vertical deviation of the tangent, vertical displacement of the tangent at A with respect to the tangent at B. This is T A to B. This is T A to B. That's it. Okay. Well, that's okay. This is something which you also understood when we read the theorem in the previous slide. Now what we need to do is just see this. Somewhere in between A and B, we will take a very small element, this dx element, right? Somewhere in between A and B, will take a very small element, x meters away from A. X meters away from A will have a very small element, something like this. You see this? Let me show that once again. Once again. This is that element. Obviously, it has slightly distorted, but remember this. Initially, the curve is like this. So this was the element dx, and now the curve is bent in this form. So the element would be something like this. So there is not much of a difference. So we can assume this also as dx. There is a bit of liberty which you can take, especially when you are dealing with calculus. Okay, you can do that. Anyway, this is part and parcel of integral calculus. You guys will get habituated. Okay. What to do now? Now listen to this very carefully. This is going to be super important, super important, and this is where most of the students get confused. Listen to this very carefully. So we drew a tangent from A, we drew a tangent from B, and this is the vertical distance. Fair enough. Now, since this is a significant portion of the beam, that is why you can see that this vertical deviation of the tangent at A is also quite significant, although it is going to be very less, right? This figure is very exaggerated, largely greatly exaggerated. Now, what we've done is we've taken this element, and let me just show that once again. This element over here, that is dx, and somewhere in between A and B, we have taken this element. Now let us draw tangent from this element also. From the left part of the element, let us make a tangent. From the right part of the element, let us make a tangent this way. What has happened? Can you understand this? This is very remarkable. Just take a look at this again. Initially, there were 2 points on the elastic curve. We drew a tangent from A, we drew a tangent from B, and this was the total vertical deviation. But if somewhere in between you take a very small element dx, and if you try to make tangents, then in between those two tangents a very small vertical deviation will appear. Let me show that once again. Tangent 1 from the left end of the element, and this is tangent from the right end of the element. A very small vertical deviation would appear, and this small vertical deviation is what we will refer to as dt. Since this entirely is t from this point to this point, since this entirely is t, from that a very small portion, okay, that is going to be dt, and let's have it, okay, and the angle subtended over here is obviously going to be d theta. Let's zoom into this. Here we go. So guys, just take a look at this. Beautiful. So starting from A and B, you can see this is the net vertical deviation from A to B, isn't it? Or deviation at A. If you take this small element, that is also going to have its own individual deviation, and it's how much? It's dt, right? And this is exactly what is going to propel us to write an equation, and let me show that what that equation is going to be. Now this is going to be, there is going to be an assumption. If you watch carefully, initially it is like this, but when loaded it is going to bend in this fashion. Initially it is like this, but when loaded it is going to bend in this fashion, isn't it? So this is point A and this is point A. So how much x distance away we took an element, this element, how much? Dx. So here, this is that dx, isn't it? As I have said, this deviation is very less, so what you can assume is, this is going to be a very safe assumption, this distance along the curve can also be assumed as x, right? This is a very safe assumption, since the curvature, or not in terms of curvature, since the deflection is going to be very small in case of beams, so what you can safely assume is that this x is equal to this x and is equal to this x. Okay, let me just show that once again and let me get out of this. Here we go, let me just show that to you. Let's try to make this. Here we go. This and this over here, the small angle, guys, this is nothing but d theta, and this can be taken as x and this can also be taken as x. Okay, let us try to see that once again. This has been assumed as x and this also has been assumed as x. That's it. If you do so, and this, by the way, is dt. Now there is something very important which I need to tell you. Remember, arc length is equal to radius multiplied by the angle between them. Okay, or you can also say this is arc length, this is very elementary, is equal to radius multiplied by the angle, an elementary formula. Okay, so how do you need to apply this? It's very clear. Arc length is nothing but dt. Dt is going to be a product of x and d theta. So what you can write is dt is equal to x times of d theta. Now some of you might be thinking as to what is d theta. So let me just show that to you. Just take a look at this. Again, let us zoom into this. So we have a tangent, and from the right end of the element we again have a tangent. Listen to me very carefully. The angle between the tangents is d theta. Therefore, the angle between the normals is also going to be d theta. So from here we'll draw a normal, and from here we'll draw a normal. Those two normals are going to intersect somewhere, and the angle again is going to be d theta. Okay, and here it is. Take a look. From this point let us draw, and from this point also let us draw. This angle over here, guys, this is nothing but d theta, and this over here, this line and this dotted line, this is nothing but the radius of curvature. You can write it as r. Okay, now you know. Just take a look at this. Again, a very interesting case, something like this. So you know this. Okay, you know this. Now the curvature is like this, and how much is this? This is dx. Let me just make a quick check. This is dx. In between this over here, that is d theta for you. That's d theta, and this is nothing but the radius of curvature. Let us write this as r. We know that arc length, that is dx. Let us take this as our equation number 1. Dx is equal to what? Radius multiplied by d theta. This is something which I had explained also in the previous session, theorem number 1. Now we are going to apply the equation of pure bending. So what can you recall from the equation of pure bending? You can recall that m over I is equal to E over R, right? So in that case R is going to be equal to, in that case R can be written as let me just write this up this way. D theta is equal to 1 by r times of dx. You can write it up this way. Okay, r comes in the denominator. So what is 1 by r? Guys, what you can see is 1 by r can be written as m upon ei. This is something which I had explained in the previous session also. You just need to plug in the value over here and that's it. So d theta ultimately is going to be equal to what? D theta will be equal to 1 by r, that is m over ei multiplied by dx simply. That's it. You need to plug in the value of d theta from equation 3 into equation 1. When you do that, this is what you are going to get from 3 in 1. When you do that, this is exactly what you are going to get, and this is going to be a fabulous expression. Let me just do that. dt is equal to x d theta, x multiplied by how much is d theta? M over ei times of dx, m over ei times of dx. Now this is going to be amazing. This is a very important result, something based on which the entire theorem is going to rest upon. Let me tell that. Okay, first of all, let me make some space. Okay. Now this is very interesting. What is this? dt is equal to x times of m over ei into dx. But what does this convey? Okay. Are you able to get the point? Let me tell that once again. dt is equal to x times of m over ei into dx. Can we get back to the slide number 5, and here we go. So if you watch carefully, we want the total deviation from this point to this point. Okay. What you need to do for that is you need to integrate. So you need to integrate within a certain range, certain allowable range. So what we'll try to do is we'll try to integrate, and we'll try to do that, integrate from theta a to theta b. When you do that, what will happen? Just take a look. Integrating this dt, okay, integrate this, and this is going to be equal to, again, this is going to be from theta a to theta b, and this is going to be x dot m over ei dot dx. Yeah, that's it. And this obviously is nothing. So from where have we taken this x distance? From a. So this is going to be ta to b, and obviously this is equal to integration from theta a to theta b, and this is x dot m over ei dot dx. Right? Can you recall something, or are you getting confused? Don't worry. If you're getting confused, don't worry. All your confusion will remove. Okay, so here is the deal. What if I tell you that this TAB is equal to x bar multiplied by this m over ei dot dx, and the limits are from theta a to theta b. Now you guys would say, sir, ye kaise ho gaya? How did this happen? Suddenly this x becomes x bar. X bar is something that we associate with centroids. Okay, isn't it? So this is going to be a very important result. Let me tell you why. Aur ye kahan se aaya? How did this result appear? What is the evidence? What is the proof? I'm going to tell you all of that thing. Okay. The transition from this integral to this integral, it's fantastic. And for that, to understand that, हमको जाना पड़ेगा इतिहास में. We need to go into the past, and this is something which we have learned in engineering mechanics. So let me just show that to you. Okay, this is going to be very interesting. We'll be very quickly, we'll get away. Let's say there is a block, uniform plate. Okay, the uniform thickness, let's say, and what's happening is the entire weight of the block must be acting at a certain point. Don't you think so? Don't you think? So if you have a block like this, right, and if you do certain pieces, then obviously all the pieces will have its own weight, but as a whole the entire weight will be acting at a certain point, and that point, by the way, is known as the center of gravity. Or you can also say center of gravity is that point where the entire weight of the system or the body is acting. That is exactly what I am trying to say. Okay, just try to get the point. right? So this is that point, this yellow color point that you see over there. It is the center of gravity where the entire weight is acting. Just try to listen to this. Weight is equal to mg. So the mass of this element, mass of this body is m. So obviously the force with which the earth is going to attract is mg. Very interesting. Now you are about to get a very quick fire revision of centroids. So this is x bar and this is y bar. Fair enough. This is centroid, x centroid, this is y centroid. Now let me just divide and rule. Okay, here we go. Okay, before dividing and ruling, what we need to do is we need to find the moment of this force. So moment of force is what? Force multiplied by perpendicular distance. You can see that if this is the force, this is the perpendicular distance. So moment of the resultant, this is the resultant force. Okay, with respect to y axis, with respect to this y axis is equal to force multiplied by this perpendicular distance, that is w into x. Yes. And then moment of the resultant with respect to y axis, just replace this w by mg, and that's it. Just listen to what I have to say. Keep on watching. Okay. Very simple stuff, very elementary. Similarly, you can take the moment about the x axis, and when you take the moment about the x axis, you need to multiply this w with a y. That's it. Now let's proceed. Let's divide and rule. Let's say this entire block is divided into n number of pieces, very small pieces, something like this, very carefully, and each piece is going to have a certain mass. Okay, delta m1, the pieces are very small, delta m2, and so on and so forth. Obviously based on that they will have their own weights also, m into g. So del m1 will have its weight as del m1 into g, somewhere here. This is, let's say, element 2. This is going to be delta m2 into g, this is going to be delta m3 into g, and that's it, this way. Now what we did in the previous slide was we took the moment of the resultant with respect to x as well as with respect to y axis. Same thing we will be doing here also, but here we don't have one single body, we have multiple bodies, right? The single body initially, it was initially a single body, but now it has been subdivided. Okay, so what we'll try to do is just try to read this equation. Moment of the resultant with respect to y axis, that means w multiplied by x bar, that means mg multiplied by x bar is equal to sum of the moments of all the small pieces about the y axis. Just take a look at this. If this is element 1, then this is x1. If this is element 2, then this is x2. If this is element m3, right, or if this is element 3, then this is going to be x3. In the same manner, what you can do is element wise you can calculate the moments. So we can write this as del m1g dot x1 plus del m2g x2 and so on. Here we go, del m1g x1, del m2g x2 and so on. For n elements you can write this, and obviously you can clearly see over to the LHS we have g, right, RHS we also have g. You can take it as common and cancel it out. This is what you are going to get. Okay, now you can express this in the summation form. It is increasing from 1, 2, 3, 4. So x is also increasing. So mixi, summation mixi, right? And you can calculate x bar from this expression. X bar is going to work out as del mixi with a summation, obviously, since there are a lot of elements, divided by m. There is a bit of integral calculus which you can apply. Let's say there are infinite pieces, right? Not n pieces, but there are infinite pieces and each piece is extremely small. In that case, this summation will convert to an integral. This delta m will convert to dm, and that's it. You can, instead of writing this m, you can also write summation of delta m. Let me just show that to you. Summation of delta m. Okay, so integration of x dm by integration of dm. That's it. This is something which you must have gone through in engineering mechanics. If you have seen my videos on centroids and center of gravity, you must know this. But in order to correlate the concepts, in order to relate this concept with that of the centroid, with that of the moment of area, I first need to make you guys understand what exactly is moment of area. क्या चीज होती है moment of area? बताते हैं. It's a mathematical expression, to be very precise. Similarly, if you do the entire analysis with respect to the x-axis, you will have y bar. With respect to the x-axis, you will have y bar, and y bar will work out as this. Now with this formula, we are going to go ahead and we are going to understand what is the moment of area. We know very well what is moment of a force. Force multiplied by perpendicular distance is moment of a force. In the same fashion, area multiplied by the centroid with respect to any line, that is the moment of area. You will get to understand this very soon. Keep watching. Don't worry. Okay. Alright. Over to the next slide. X bar. We know very well what X bar is. So if I were to spread it up, I can write it as m1 x1, m2 x2, m3 x3 and divided by m1 plus m2 plus m3, isn't it? Isn't it? Like this for all the elements. Now, just take a look at this. This is going to get super interesting. Just take a look. Okay, we have written it like this. Now what we'll do is, you see this element popping up? Let me tell you. Let's say that the thickness, okay, where should I make this? Let's say that this element over here is having a thickness T. So an element pops up like this, and let's say that the density is rho. Thickness is T and the density is rho. This area is A. Instead of doing this, let me just hatch it. The area is A, the thickness is T, so the volume is going to be area multiplied by T, right? All the elements are going to have the same volume, A multiplied by T. A is the cross section, upper cross section, you can say this. A multiplied by T will give you the volume. But how can that help us? And secondly, this over here is nothing but the density. Density is rho. Now you must know this, density is equal to mass over volume. So mass is equal to density into volume. And this is going to be very helpful. Density, keep it as it is, rho, and volume is nothing but A into T. This is going to be super helpful for us, right? Watch this. So as I told you, density multiplied by area multiplied by thickness. Density, it's a very small area, delta A1 for element 1, let's say, and this is going to be thickness. Thickness is common for all the elements, for all the small, infinitesimally small elements. And you just do this for M2, rho delta A2 into T, for Mn, rho delta An into T, and similarly in the denominator, make the same substitution. Now guys, watch. T can be taken from the numerator, T can be taken as common. Also rho can be taken as common. Rho and T can be taken as common from numerator as well as denominator, and they'll cancel out. What shall remain is this. I need to make space. Okay? You'll get the entire idea, don't worry. As a teacher, things take a bit long to understand, but once you understand the concept, once you grasp the concept, it will be very easy for you to apply and solve the problems, right? So keep watching. Here we go. Now let us write it in the summation form. Okay, so from mass we have converted to area, and you can clearly see if you do infinite pieces, this summation will convert to integral, this delta A will convert to dA, and that's it. Let us write this in the integral form. This is what I was trying to say. Okay, and this expression over here, this x dA over here is nothing but the moment of area, and this is where, or this is how moment of area comes into the picture. Remember this integral of x dA is nothing but the moment of area. Okay, anyway, so that was all logic, and similarly you can calculate y bar also, right? Let me just write this. Why not write this? Integral of x dot dA is equal to x bar integral of dA. It's a very wonderful expression. Now how can we relate this with this? You have completely understood how we reached here, but suddenly from this integral of x dot m over ei dx, how did I write this one? You will get to understand this very soon. Okay, so here we go. Let me make some space, right? Kidhar gaya kala? Ithe. Just take a look at this. I'm going to be making two figures. This and one more figure. This is something that you have learnt at school. This is y and x, and here also we have x axis, but in the y axis we have this M over EI. Obviously, we took the case of a simply supported beam, so the bending moment at the ends is going to be 0. So bending moment banai. Bending moment, guys, just take a look. Where are the bending moments? The bending moment diagram would be something like this. Pretty bad. Okay, and somewhere in between, this is going to be our point A and that's going to be our point B. Just let us try to correlate it. Similarly, we'll have a figure over here. Okay, this is a hypothetical case and we are going to have 2 points. That's point A and that's point B. Just try to understand. Okay, randomly I have made this. Now, if I take a very small strip over here, very small rectangle, the thickness of the rectangle is extremely small, right? When it is extremely small, what do we call it? We call it dx. How much away? X distance away. Okay, you should recall this. Okay, x distance away, we took an element dx. And the area of this element, if I were to calculate the area of this element, it would be, so let's say the height is y, so the area of this element is going to be y dot dx, isn't it? Area of the strip is y dot dx. In the same fashion, we can represent this area also. Just take a look. So how much away from A? X distance away from A, we took a very small element. This element is dx, and obviously this area is nothing but this height multiplied by dx. So this area is how much? This height is how much? That is, here it was y and here it is going to be m over ei. M over ei, and this distance is how much? That is dx. So that is the area. So one thing is clear, if you want to integrate from A to B, if you want to integrate, let me tell that once again. Okay, if I write it like this, integration y dx from A to B, what do I exactly mean geometrically? I mean this area, right? And when I write it like this, integration from A to B, m over ei dx, m over ei dx, we are sliding this from A to B. That means again we are going to cover the entire area. Now that means one thing is for sure, that this over here represents the area under the m over ei diagram. But what the hell is this x bar? Let me reiterate. This m over ei dx and with an integration sign represents the area under the m over ei diagram between point A and point B. But the confusion is, what is x bar? Let's see that. Okay, some of you might have guessed even. What is x bar, right? Anyway, I'll let you know what that is. It's going to be very simple. Just take a look at this. Now we know that x dot dA is equal to x bar dA, don't we? You've seen that very. Kidhar gaya? You've seen this. X bar multiplied by integral of dA is equal to x dot dA. Okay, and this is exactly what I've written. In the same fashion, in place. Just take a look at this. In the same fashion, here x, just try to compare x. Okay, dA, this is what? This is nothing but area of rectangular element. The width of which is dx. The width of this rectangular element is nothing but dx. Okay, so x multiplied by this dA is nothing but this m over ei dx, m over ei dx. You should understand this, m over ei dx. And going back to history, okay, you also know if this is the case, then obviously this can be equated to x bar multiplied by m over ei dot dx. Okay, that's it, and this is exactly why I have written it in this fashion. That is the entire idea. Okay, that is the entire idea. Now let me try to further simplify stuff, and so that things might become a bit more clear. Let me show that. Okay, here we go. Let's say initially the beam was like this, then it bent. Okay, here we go. We've got 2 points, point A and B, So if you draw the bending moment diagram, right? If you draw the bending moment diagram like this, that's X for you, and this is not the bending moment diagram but the M over EI diagram. So it's going to be something like this, isn't it? And if you draw a tangent at A, and if you draw a tangent at B, and this obviously is the vertical deviation at A, and this obviously is the vertical deviation at B. And if I were to write this, okay, I'm summarizing everything. Vertical deviation at A can be written as T A by B or A to B, and this can be written as T P to A. Now, if you want to calculate this, what needs to be done? Let me tell you. Okay, very interesting. Keep watching. If you want to calculate this, that's A and that's B. So if you want to calculate TA to B, what we shall write is this. That is the area first of all which you need to calculate. Okay, let me write it over here. TA to B is equal to what? X bar is nothing but the centroid. What is that X bar? Let me clarify. Let me clarify. That's the X bar I'm talking about. X bar. That means whatever figure, plane figure this is, you need to find its centroid. And it is that centroid, X bar, multiplied by this integral. This integral represents the area under the M over EI diagram between point A and point B. That's it. Area under M over EI diagram between point A and point B. Let me just write this. M over EI dot what? Dot dx. Okay, that's it. Now let's say you want to find the vertical deviation at B. What needs to be done? In that case, let me just write this. Vertical deviation at B. Okay, we need to find the vertical deviation at B. T B to A. This will be equal to again an X bar, right? This is the X bar I'm talking about. For A to B, for B to A, the X bar is going to change. Okay, in that case, since you want to find the vertical deviation at B, again the area is going to be same. This is going to be same, but this is the X bar which you need to take. Let's say X dash bar. This is going to be X dash bar, and again the area is same from A to B, and that's M over EI dot dx. That's it. This is the entire idea of calculating the vertical deviation at any point on the elastic curve. To sum it up, you can write it like this. T A to B is equal to what? Is equal to centroid measured. Write this formula. This is going to be super awesome. Centroid measured from A multiplied by the area under M over EI diagram. Okay, between points A and B. Between A and B. And in the same fashion, you can write this. T B to A is equal to centroid measured from here. It is going to be B multiplied by area under an M over EI diagram. Everything is going to remain same. These two formulas are the juice, right, of what we've learned till now. The entire concept of theorem number 2, which was based on vertical deviation or vertical displacements, right? So the session might have become a bit too long, but what to do? Things are so complicated that you have to put it up this way. Everything has a story. Every concept has a story. वो होता है ना movies में हर character का एक ना एक पीछे का story होता है. So it's like this. So if I had straight away written from this step, if I've straight away gone to this step, आपको कुछ समझ नहीं आता. You wouldn't have been able to understand anything. So the entire story was based on the concept of centroid and center of gravity. I had to explain that. I had to explain to you what exactly moment of an area is. Okay, and this over here is nothing but area. Okay, as I've told you, m over ei dot dx from theta a to theta b represents an area, and that area when multiplied by the centroid is the moment of an area. Right, getting the concept? Now let's get ready to solve some problems. Let's work them out together. So guys, the first problem, the first example that we are going to take on will be based on a cantilever beam, and we shall try to find the deflection at the free end. Let me just show that to you. It's like this. Okay, so it's a cantilever beam like this. Beautiful. And this beam actually carries a moment over here, and let's say the magnitude will be represented by m naught. The length of the beam, let's say, is represented by L. What we wish to calculate is, and this by the way is absolutely fixed, this is end A, fixed end, this is free end, that is end B. What you need to work out is the deflection at B. Okay, find the deflection at B. How do you wish to accomplish this? Well, we are going to be using this formula. This is going to be super helpful for us. Okay, whenever you come across any problem, straight away make the elastic curve. How would it bend? It would bend something like this. Obviously, this is just try to work out the nature. It would bend the beam in this fashion. Okay, if this is the fixed end, it would bend the beam in this fashion. If I can just extend this hypothetically, this is sort of what you call a hogging bending moment, isn't it? Don't worry, I'll explain. Sort of a hogging bending moment, a negative bending moment to be very precise. So if we can just extend this, okay, and this is point A, and if it is supposed to bend, it would bend in this fashion. Yeah, and this, by the way, is gonna be your customary point B, and that's point A. And if I were to draw the tangent at A, it would be something like this. That's tangent at A. Okay, why am I drawing this? You'll get all the answers, don't worry. And this is, by the way, point B, right? We want to find the vertical deflection at B, okay, and that is going to help us. And drawing a tangent is going to help us. Okay, extending it backwards. Yeah, this is going to do the job for us. So this is going to be tangent at B. And this over here, कैसे बनाए? लाल से बनाए. This over here, what you need to find is, you need to find the deviation at B. That means deviation at B with respect to A. TB to A is supposed to be calculated, and this is the deflection at B, right? This is nothing but the deflection at B. But कैसे करें calculate? बताते हैं आपको. Bending moment diagram तो आपको बनाना ही है. You need to make the bending moment diagram and divide it by EI to make the corresponding M over EI diagram. So watch this. With practice, you can solve the problems very quickly. Let's say this is the positive x-axis, not positive x but positive y-axis, and this over here is M over EI. Remember, bending moment diagram and M over EI diagram, they are proportionally, if you draw the bending moment diagram, it is proportionally bigger than this. Okay, don't worry. So this is going to be your positive x-axis, and then if you take a look, what you need to work out is the bending moment at all the points of the beam. Then only will you be able to make the bending moment diagram. But how? Again, beam, fixed end, free end carries the bending moment, name is m naught. Let's say we want the bending moment somewhere here at this particular point. Okay, so there is no force acting. What to do? There is only one bending moment, and that too, this is trying to bend the beam in clockwise sense, or let's say it is trying to bend the beam in this sense, hogging sense. That means a negative bending moment. Wherever section you take, The idea is wherever you take this section, you are going to get a negative value of bending moment. And let me prove that with the help of method of section also. Let's say we have taken the section from the right. Only this much portion of the beam we will consider. This is going to be m0, and let's say when you take the section from the right, the moment at this section is mx. So when you take the moment about this point, when you take the moment about this point is equal to 0, what you have is this is clockwise, so minus mx, and this is also clockwise. What you will get? Again minus m0, and this is going to be equal to 0. So mx is going to work out as minus m0. Now listen to this very carefully. This bending moment is actually independent of x. No matter where you take the section, it might be here, here, here. Section किधर भी लेने का bending moment कितना आएगा? The bending moment would always be equal to minus of m0. Does not matter where you take this section, the bending moment is always going to be minus m0, and that is the proof. Okay, through the method of sections. Now, what we'll try to do is, that means at every point here, 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 everywhere the bending moment is going to be same. And where does the beam end? Somewhere here. Let me make it like this. Beautiful. And since all the values are negative, guys, this is nothing but minus m0. All the values are negative. That is a clear indication. It's a clear-cut case of a negative bending moment. So that was the entire story. As I told you, every character has its own story. ये थी पूरी कहानी. Okay, now what? Just take a look. What do you need to find? You need to find TB2A. Okay, TB2A, right? TB2A. TB2A is equal to x bar. So that's A, that's B, and so we need to work out this negative area. Okay, we can calculate that very easily. You know, this obviously represents the length of the beam, that's L for you, and this is nothing but what? M0, but with a negative sign. Okay, so this area can be easily determined. That's quite easy. X bar multiplied x bar multiplied by the area under M over EI diagram between the points A, B. Let me just write this as B dash, and let me just write this as A dash. Okay, so you're working between A and B, A and B, so area also has to be taken between A and B of the M over EI diagram. A, B, A dash and B dash, right? And x bar, where do you wish to find a displacement or vertical deviation? You need to find it at B. So x bar has to be measured from B itself. Remember, this is going to be very important. This is a symmetrical case, so no need to worry, but you are going to come across some different sorts of geometries, and there this knowledge of x bar is going to come in very handy. Anyway, so we know very well the centroid is going to be somewhere here. This is the centroid. Let me just write this as CEN, right? Where do we need to measure the centroid from? From B. So if you watch, that's x bar is equal to what? L by 2, and that's it. You know what x bar is. How much is it? It's L over 2 multiplied by the area. It's quite simple. Minus m0 multiplied by L. So that's minus m0 multiplied by L. And by the way, I forgot to write this. This is not just m0. This is m0 over EI. Okay, this is m0 over EI. Right? m0 over EI. Whatever bending moment value you get, so in order to put it up in the m over EI equation or diagram, you just divide it by EI. Anyway, so this is our final result. So TB2A, that is the deflection at the free end, by the way, is minus m0 L square divided by 2 EI. I forgot to write this. EI. Brilliant. Let me just make a quick check. Minus m0 L square upon 2 EI. Okay, understood the point? Let's take up one more example again of a cantilever beam. Let's see if we can work it out or not. Always remember, wherever you want to find the displacement, if the displacement is supposed to be found at A, the distance of the centroid has to be taken from A. If the displacement is to be found at B, the distance of the centroid has to be taken from B. Remember this. This is going to be very helpful. Second problem, and you can actually verify using Macaulay's theorem also. All these formulas have been derived in my previous lectures based on double integration, based on Macaulay's method. Let's say we've got a point load over here, concentrated load, that is P. And let's say that this is fixed. Let me call this A, let me call this B. What we wish to find is the deflection at this free end. Kaise nikalenge? For that, what we need to do is we need to draw an elastic curve. So the elastic curve would be of this fashion, isn't it? Okay. So this is point A. This right here is point B. And if I were to draw the tangent at A, it would be something like this. This is nothing but the tangent. Tangent at A. Now, since I have to calculate deflection at B, so I have to make the tangent at B on this elastic curve. How do you wish to do that? Like this, touch and go. Okay. And if you watch this over here, it is in the downward direction. Okay. The downward direction means that the answer that you are going to get will be negative. Here also, it was in the downward direction, and that is why we got a negative sign. Same here also, you will get a negative sign. Okay, in the final answer, you will realize this. Okay, so this is tangent at A, and this right here is the tangent at B. Fair enough. Okay, one thing is left, just make the bending moment diagram. That's also quite simple. Let's say this y-axis represents the M over EI, right? Let me have the x-axis. That's the x-axis. Extend this. As you can see, the beam bends in this fashion. What is this? This is a clear-cut case of hogging, negative bending moment. So this is quite clear. At the fixed end, you are going to have the maximum bending moment. Let's say this length is L. So P multiplied by L will give you the value of maximum bending moment. So over here, the value is going to be PL. It is PL, but you need to divide that by EI. Since it is of a hogging nature, and therefore you need to put a negative sign. And similarly, if you want the bending moment here, you need to multiply P multiplied by L by 2. If it is at the center of the beam, then it is going to be P into L by 2. But again, hogging nature, negative sign. So everywhere. So if you keep on joining all those points, the curve which you are going to get finally, where is the final point? Somewhere here. The curve which you are going to get would be something like this, right? And again, negative, negative, right? How much is this length? That's L. Okay, what do we wish to calculate? Okay, this is your example number 2. What do you wish to calculate is YB. What is YB? Right? Tangent at B. Vertical deviation of tangent at B with respect to tangent at A. Okay, that is T, vertical deviation of tangent drawn at B with respect to another tangent drawn from A, TB to A, and TB to A, by the way, is your deflection at B. How do you calculate this? Nothing but centroid multiplied by the area. Area of what? Let's say this is A, let's say this is B, let's say this is A dash. Area between area A, B, A dash from this M over EI diagram. This is the area I am talking about. Right? This is the area I am talking about. And as far as this X bar is concerned, guys, remember, for a triangle, I don't know whether you know this or not. If this is A, let's call this as A. If this is B, then this is the centroid G. This is going to be A by 3, and this over is going to be B by 3. That means from the right angle, it is A by 3 and B by 3. And similarly, here also, somewhere here, let me rub these lines. Let me tuck this negative sign also. Somewhere here we are going to have the centroid. Okay, at this distance, how much is this? This is going to be L by 3. I hope this is visible, right? If this is L by 3, from where do you need to measure this x bar? You have to measure from B. Remember, these are all the small things which you need to remember. Measured from B. Why? Because it is TB to A. Had this been TA to B, then you would have to measure it from A. Anyway, you need to know this measurement. So how much is this? L minus L by 3. Obviously, this is going to be 2L by 3. And there you go. We have all the values. You just need to plug it in over here. X bar is how much? That is going to be 2L by 3 multiplied by area. Area is nothing but half of base into height. So half of base is how much? That's L into height is how much? Minus of P L over E I. And there you go. You again have an expression. The deflection at point B is going to work out as, let me just check, L P L cube over 3 EI. 2 and 2 will cancel out. So this is going to be equal to minus P L cube over 3 EI. And this is exactly how you can apply theorem number 2 of the moment area method to get the value of deflection at any point on a beam. Beam could be any, it could be a simply supported beam or a cantilever beam or even an overhanging beam. So guys, yes, that was all for today, and let me make a promise. We'll be taking some tough and uncomfortable questions, and we'll be applying the moment area method to find the slopes and deflection at distinct points on that beam. So that was all for today. I'm going to see you again in the next video. Until then, take care, have a nice day, keep learning, keep watching, and thank you.